Now you may be asking yourself, is there an easier way to solve this complex network? And yes, there is. Turns out that I can rewrite that equation 1 to be equal to negative 2I1 plus 0I2 plus I3 is equal to negative 13. I can rewrite equations 2 and 3 to look like 0I1 minus 3I2 minus 2I3 is also equal to negative 13. And then I can say negative 1I1 plus I2 minus I3 must be equal to 0 for my third loop. It turns out that we can express this in matrix form simply by saying that this is going to be negative 2, 0, and 1. And we're going to have 0 minus 3 minus 2, negative 1, 1, and 0, multiplied by my matrix I1, I2, and I3. These are my three currents. It's going to be equal to negative 13, and 0. So this is really kind of saying A multiplied by I is equal to B. If we want to solve this guy for I, what we do is we say multiply both of these guys by the inverse of A on the left hand side. It's going to be equal to A inverse multiplied by B. That tells me that I can write my matrix of currents as equal to the inverse of A multiplied by B. So I can say that my matrix of currents, I1, I2, and I3, is going to be equal to the inverse of A. The inverse of A, if you could do this using row reduction or a handy dandy online calculator, it's going to be negative 1/13, negative 5, negative 1, negative 3, negative 2, negative 3, and 4, and then 3, negative 2, negative 6. Multiply that guy by matrix B, negative 13, and 0. So you multiply those matrices together, and you're going to come out with 6, 5, and negative 1, 6 being I1, 6 amps being I1, 5 amps being I2, and negative 1 amps being I3.